Welcome to the fourth session of the circular function series. In this session, we will continue to demonstrate how to apply compound angle formula and identity relations to simplify and solve trigonometric functions. We will also learn how to use the general solution form of sine, cosine, and tangent functions to express angles. We will demonstrate 6 worked examples in this session.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything.
Welcome to the fourth session of the circular function series. Here, example 1 is to prove the sum of arctangent 1, arctangent 2, and arctangent 3 equals pi, given that all the angles are in radians. We start by moving the term arctangent 3 to the right hand side of the equation. Then we take tangent function on both sides of the equation and then see if they are equal. From the left hand side of the equation, we expand the tangent of the sum of arctangent 1 and arctangent 2 using the tangent addition formula. So it equals 1 plus 2 all over the result of 1 minus 1 times 2, which equals negative 3, as it can be seen on the screen. However, on the right hand side of the equation, since tangent pi minus arctangent 3 can be transformed to negative tangent arctangent 3, which actually is negative 3. From the above, we have proved that the sum of arctangent 1, arctangent 2, and arctangent 3 equals pi. Example 2 is to find the expression of the general solution for the equation of sine x plus 2 cosine x equals square root 5. First of all, we need to simplify the left-hand side of the equation to a single trigonometry function using addition formula. By doing so, we need to times and divide it by a number of square root 5, which is calculated by the square root of 1 squared plus 2 squared. Then we assume an angle theta and let it equal to arc cosine 1 over square root 5. Hence, cosine theta equals 1 over square root 5 and sine theta equals 2 over square root 5. After applying the sine addition formula, we have sine x plus theta equals 1. According to the general solution for sine function, we have x equals n pi plus negative 1, or in parentheses to the n, times pi over 2 minus arc cosine 1 over square root 5. After being further simplified, x is expressed to 2n pi plus pi over 2 minus arc cosine 1 over square root 5. Here n is an integer. Example 3 is to evaluate tangent alpha plus beta, given that sine to alpha equals 3 over 5, tangent alpha minus beta equals 1 over 2, where angle to alpha is in the second quadrant. According to the given criteria and the Pythagorean identity relation, cosine to alpha equals negative square root of 1 minus sine squared to alpha, which equals negative 4 over 5. Hence, tangent to alpha equals the ratio of sine to alpha to cosine to alpha, which is negative 3 over 4. Since alpha plus beta can be written to 2 alpha minus open bracket alpha minus beta close bracket. So tangent alpha plus beta can be written to tangent open bracket to alpha minus open bracket alpha minus beta close bracket close bracket. Up to this point, we may apply the tangent compound angle formula to express tangent alpha plus beta in terms of tangent to alpha and tangent alpha minus beta. Since we have known the values of tangent to alpha and tangent alpha minus beta, after substituting their values in the expression of tangent alpha plus beta, we obtain its value, which is -2. Example 4 is to solve three simple circular functions given that x is between 0 and 2 pi. Here we apply the general solution forms for sine, cosine, and tangent functions, and you may learn how to use this technique to solve similar questions. As for the first equation, since tangent x equals -√3, then x equals n pi plus arctangent -√3, which can be simplified to x equals n pi minus pi over 3, where n is an integer. This is the general solution for the x, and based on that, we may take different values of n to find the corresponding x value. However, in this question, since the domain is between 0 and 2 pi, the values of n we can take is depend on the restriction of the given domain. So we find x equals 2 pi over 3 when n equals 1. X equals 5 pi over 3 when n equals 2. As for the next equation, after applying the general formula for sine function, we have x equals n pi plus -1, or in parentheses to the nth, times arcsine -√3 over 2, or in parentheses. After being simplified, the general solution becomes x equals n pi plus -1, or in parentheses to the power of n plus 1, then times pi over 3. Hence, x equals 4 pi over 3 when n equals 1. X equals 5 pi over 3 when n equals 2. Here n is an integer. As for the last equation, since cosine x equals 1 over square root 2, after applying and simplifying the general solution of cosine function, x equals 2n pi plus or minus pi over 4. Hence, x equals pi over 4 when n equals 0. X equals 7 pi over 4 when n equals 1. Example 5 has 6 circular function equations to solve, given that the angle theta is between 0 and 2 pi, including the left end point. As demonstrated in the previous example, we still applied the identity relations to solve these equations, as well as use the general formula forms to express the solved angle theta, and then we will choose the number n according to the value range of the angle theta. As for the first equation, since cosecant squared theta equals cotangent squared theta plus 1, the equation can be rearranged and factorized to 2 times cotangent theta plus square root 2, or in parentheses times cotangent theta minus square root 2, or in parentheses equals 0. So when cotangent theta plus square root 2 equals 0, we have the general solution form for the tangent function. Theta equals n pi minus arctangent square root 2 over 2. And based on that, theta equals pi minus arctangent square root 2 over 2 when n equals 1. Theta equals 2 pi minus arctangent square root 2 over 2 when n equals 2. Now, When cotangent theta minus square root 2 equals 0, we have the general solution form for the tangent function theta equals n pi plus arctangent square root 2 over 2. And based on that, theta equals arctangent square root 2 over 2 when n equals 0. Theta equals pi plus arctangent square root 2 over 2 when n equals 1. Finally, we summarize the 4 theta values that satisfy the equation. Here we continue to work on equation 2 of example 5. Since sine squared theta can be replaced by 1 minus cosine squared theta, then the equation is reduced to cosine theta times cosine theta minus 2, or in parentheses, equals 0. Since cosine theta is less than 2, the solution lies in the equation of cosine theta equals 0. Hence, we apply the general solution for cosine function and obtain that theta equals 2n pi plus or minus arc cosine 0, which equals 2n pi plus or minus pi over 2. Based on that, we may obtain the values of theta, which equals pi over 2 when n is 0. Theta equals 3 pi over 2 when n is 1. As for question 3, since secant squared theta equals tangent squared theta plus 1, the equation can be reduced to 4 tangent squared theta minus 3 tangent theta plus 1 equals 0, which is factorized using the cross product method. Then we apply the null factor law to find the values of theta. When 4 tangent theta plus 1 equals 0, the general solution shows that theta equals n pi minus arctangent 1 over 4. Accordingly, when n equals 1, theta equals pi minus arctangent 1 over 4. When n equals 2, theta equals 2 pi minus arctangent 1 over 4. When tangent theta minus 1 equals 0, the general solution shows that theta equals n pi plus arctangent 1. Hence, when n equals 0, theta equals pi over 4. When n equals 1, theta equals 5 pi over 4. Finally, we summarize all the theta values that satisfy the equation. Here we continue to work on equation 4 of example 5. As it can be seen on the screen, the equation of cotangent theta plus tangent theta equals 2 can be transformed to tangent squared theta minus 2 tangent theta plus 1, all over tangent theta equals 0. Since the numerator is a complete square, tangent theta minus 1, or in parentheses squared, equals 0. Hence, the general solution for tangent function is applied here, and theta equals n pi plus pi over 4. Based on that, we obtain the values of theta, that equals pi over 4 when n is 0. Theta equals 5 pi over 4 when n is 1. As for equation 5, since cotangent squared theta equals cosecant squared theta minus 1, the equation is reduced to its quadratic form of 6 cosecant squared theta plus 13 cosecant theta minus 8 equals 0, which can be factorized and then apply the null factor law to obtain the required theta values. Since the modulus value of cosecant theta is greater than or equal to 1, cosecant theta only equals negative 8 over 3 in this case. Hence, we obtain the expression of general solution of sine function, in which theta equals n pi plus negative 1, or in parentheses raised to the power of n plus 1, times arc sine 3 over 8. Hence, when n equals 1, theta equals pi plus arcsine 3 over 8. When n equals 2, theta equals 2 pi minus arcsine 3 over 8. Here we continue to work on the last equation of example 5. The first step is to replace sine squared theta by 1 minus cosine squared theta. The equation now is reduced to its quadratic form and factorized. Then we apply the null factor law to obtain the values of cosine theta that satisfy the equation. When 2 cosine theta minus 1 equals 0, theta equals 2n pi plus or minus arc cosine 1 over 2. So theta equals arc cosine 1 over 2 when n is 0. Theta equals 2 pi minus arc cosine 1 over 2 when n is 1. When cosine theta plus 1 equals 0, theta is expressed to 2n pi plus or minus arc cosine negative 1, which equals 2n pi plus or minus pi. So in this case, theta equals pi when n equals 0. In conclusion, 3 theta values are obtained. They are arc cosine 1 over 2, 2 pi minus arc cosine 1 over 2, and pi. Example 6 is to find the maximum and minimum values of a given circular function. Y equals 3 sine x cosine x minus 4 cosine squared x. In order to achieve the targets, we need to take 2 steps to transform the function to one single trigonometry function. Now, let me explain how we do it. First, taking out the common factor cosine x. The remaining parts inside the parentheses are 3 sine x minus 4 cosine x. At this point, the function is multiplied and divided by the same number 5. And then we assume cosine theta equals 3 over 5. Then, accordingly, sine theta equals 4 over 5. After being applied the common angle formula, the function becomes 5 cosine x times open bracket sine x cosine theta minus cosine x sine theta close bracket, which equals 5 times sine x minus theta cosine x. Now we need to apply the product to addition formula, which has shown in red color here. Here alpha is regarded as x minus theta, beta is regarded as x. Hence, y equals 5 over 2 multiplies open bracket sine x minus theta minus x plus sine x minus theta plus x close bracket. After being further simplified, the function y equals 5 over 2 multiplies sine 2x minus theta minus 2. Since sine 2x minus theta is between negative 1 and 1, including both endpoints, the minimum value of y equals negative 9 over 2, while the maximum value of y equals 1 over 2. Here we continue to work on the alternative approach of example 6. With this approach, we use the double angle formula to transform cosine squared x to 1 plus cosine 2x all over 2. Hence the function becomes 3 over 2 times sine 2x minus 2 cosine 2x minus 2. In order to apply the addition formula, the first 2 terms are multiplied and divided by the same number, 5 over 2. Then the function becomes 5 over 2 multiplies open brackets 3 over 5 times sine 2x minus 4 over 5 times cosine 2x close bracket minus 2. At this point, we assume cosine theta equals 3 over 5 and accordingly sine theta equals 4 over 5. Hence, the function equals 5 over 2 multiplies open bracket sine 2x cosine theta minus cosine 2x sine theta close bracket minus 2, which equals 5 over 2 times sine 2x minus theta minus 2. Since sine 2x minus theta is between -1 and 1, including both endpoints, the minimum value of y equals -9 over 2, while the maximum value of y equals 1 over 2. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.